All right, let's continue with the session. We actually have a double feature by Satoshi now. He will be giving 2 talks in a row. The first one is on the one-to-one correspondence between deterministic port-based teleportation and unitary estimation. Please.
Thank you very much for the kind introduction. So I'm Satoshi Yoshida from the University of Tokyo, and in this first talk, I will talk about something about port-based teleportation and unitary estimation. And this talk is based on the archive paper shown here, and this is a joint work with Yuki and Michał and Michał and Murao. Okay. So first, I will talk about what this talk is about. So in this talk, I will consider two tasks. One task is called port-based teleportation, and basically it's a task of teleporting some unknown quantum state from Alice to Bob. And for this teleportation, we can define the teleportation fidelity as a figure of merit. And the other task is called the unitary estimation, and basically it is an estimation task. If you have some unknown interpolation, this is a task to estimate what this unitary is. And for this one, we can define the estimation fidelity. And these two tasks are seemingly unrelated, but basically in this work, we have constructed a conversion between 2 protocols. And basically in this conversion, the fidelity of each protocol does not decrease. So by using this conversion, we can show that the optimal fidelity for these tasks are actually equivalent. And in this way, so this is kind of showing the equivalence between 2 tasks in a constructive way. Okay, so let's begin. So first, I will talk about what the port-based teleportation is. And to explain that, I will first introduce the task of universal programming of unitary operation. And this is a task to encode the information of channel to the state, which is called a program state. And the task is, if you have this program state, and by applying the quantum channel with the input state and the program state, you want to retrieve the encoded quantum channel U. But unfortunately, there is a no-go theorem prohibiting this implementation, and it is shown that universal programming is impossible. So we can just consider the probabilistic or non-exact implementation. And to implement that probabilistically, we can utilize the teleportation. So usually, quantum teleportation is to implement the identity channel from the Alice to Bob. But and this is done by preparing the Bell state between Alice and Bob, and do a Bell measurement, and then send the classical information to Bob, and then do a power correction to obtain the quantum state. And if we replace the maximal entangled state shared between Alice and Bob with the choice state of the unitary operation U, then we can basically do a universal programming. Why? Because if you apply U on the maximal entangled state, then the state that Bob gets is basically represented by U followed by the Pauli errors. And if the Pauli measurement outcome is 0, 0, then Bob will get the state U xi. And then in this way, we can implement the universal programming. So the lesson from this example is that retrieval succeeds when the Pauli correction is not needed. And basically, port-based teleportation is a teleportation without the Pauli correction. And to implement that, we pay additional cost of the entanglement instead. And in this task, so basically, Alice and Bob have a 2n qubit state instead of just a 2 qubit state. And Alice do a measurement and send the measurement outcome to Bob. And in the correction stage, Bob just do a very simple operation, which is to choose ith quantum state what Bob has. And Bob doesn't need to do any Pauli correction. And since there is no correction, we can do a retrieval in this port-based teleportation. And basically, by applying the quantum channel epsilon on this entangled state psi, we can implement the universal programming. Okay, and this is the known result for the port-based teleportation and the universal programming. And the first thing is that for the probabilistic case, everything is basically known. So it is known that optimal probabilistic universal programming is done by port-based teleportation. And its optimal success probability for each dimension d and number of qubits n is also known. So it scales like like this. But for the deterministic non-exact case, less is known. And it is known that optimal universal programming is achieved via unitary estimation, but it is basically the different task from the port-based teleportation. So the connection between universal programming and the port-based teleportation is not known, and also its optimal fidelity is not known. So the natural question here arising is that is there any connection between this unitary estimation and the port-based teleportation? Because it is already known that universal programming is the same as unitary estimation. So it's kind of natural question to rewrite these two tasks. Okay, so this is the outline of this talk. So first I will define the task more formally, and then I will show you the main result and the applications and the proof techniques used in this construction, and I will conclude the talk. Okay, so first, for the port-based teleportation, basically, Alice and Bob shares a 2n qubit entangled state. And here, I write it as a phi PBT. And after that, Alice do a measurement given by a P of m pi a. And depending on the measurement outcome, Bob chooses the S quantum state. So in the quantum circuit, it is basically represented by a right figure. And by using this quantum circuit, we can define the teleportation channel, which basically represents the channel from Alice to Bob. And the fidelity of this task can be evaluated by the channel fidelity between this teleportation channel and identity. Okay. And for the unitary estimation, the task is as follows. So you have some unknown unitary operation, which is drawn from the Hall random distribution. And you can query n times. And the task is to estimate what this unitary is. And basically, what the estimator can do is basically represented by the right quantum circuit. So you can just prepare some state, and you apply the unitary on that. And after that, you will you will apply the measurement. And from this quantum circuit, so basically the guessing probability is represented in this equation. And basically we define the figure merit as an average case of channel fidelity between the input unitary operation and the estimated unitary operation. Okay, so I will show you the main results. So in this work, we have constructed a one-to-one correspondence between port-based teleportation and the unitary estimation. And to be more precise, it's an equivalence between port-based teleportation d-dimensional port-based teleportation with n+1 ports, and d-dimensional unitary estimation using n queries. So we have shown that the optimal fidelity of the port-based teleportation for this case and the optimal fidelity of the unitary estimation for this case is equivalent. So it's basically the equivalence. And additionally, we have constructed the explicit conversion from one protocol to the other, as shown like this. So we have constructed the conversion explicitly. And and before going to the proof techniques, I will briefly talk about some applications of this work. So first, basically, by using this equivalence, if we know something about the port-based teleportation, we can just translate this result to the unitary estimation and vice versa. So basically, we can use this equivalence in this way. And the first application is to translate the result from the unitary estimation to the port-based teleportation. So in the unitary estimation, its optimal fidelity is known to be obeying the Heisenberg limit. So it scales as 1 over n squared for the number of queries n. And the coefficient of n squared is also known, and it's known to be d to the fourth. And basically, we can just translate this result to the port-based teleportation. So we can show that the optimal fidelity of port-based teleportation also satisfies the same Heisenberg limit, and its coefficient is also determined. And I remark that its Heisenberg limit is already shown in the previous result by Matheus Crisciando et al. But our result improves over this result in terms of the coefficient. So in the previous work, the coefficient of the 1 over n square is, it just determines the lower bound and upper bound for the coefficient of the 1 over n square, which is given by O to the d to the 5 and then d to the 2. But by using our equivalence, we can determine its dependence on d exactly. And it also partially solves the open problem to determine its coefficient raised in the previous work. Okay. So the second application is to translate the known result of port-based teleportation to the unitary estimation. So for the port-based teleportation, if the number of ports is small, then its optimal fidelity is already known by using some group theoretical analysis. And we can just translate this result to the unitary estimation. And in the world of unitary estimation, basically, if you have a small number of queries, then its optimal fidelity can be exactly determined. So the optimal fidelity for this case is given by this equation. So it's basically scale linearly with the number of queries n. And additionally, we can also show that if we look at the optimal resource state for the port-based teleportation and for the unitary estimation, we can also show that these are actually equivalent, or the same. So it also implies some interesting feature that there may be some universal resource state which can be applied for port-based teleportation and the unitary estimation at the same time. Okay. So final application is about unitary inversion. It's about the third task. So unitary inversion is a task to invert the unknown unitary operation. So the setting is a bit similar to the unitary estimation. So you have some unknown unitary operation which is drawn from the Hall random distribution. But the task is different. So the task is to implement the inverse of unitary. And we can consider some strategies to implement this inversion, which is just to utilize input unitary in parallel or sequential or even using indefinite causal order like quantum switch. But by using the optimal estimation result shown in the last slide, we show that actually parallel and the sequential and indefinite causal order protocol gives you the same fidelity. And it's actually the same as the estimation fidelity. So in this regime, we have shown that measure and prepare is actually the optimal for this regime. Okay, so in the remaining time, I will talk about the proof technique, how to construct this conversion from port-based teleportation to the unitary estimation. Okay, so the proof goes in the 2 steps. So the first step is that by using the symmetry of the program, any protocol implementing the port-based teleportation or unitary estimation can be converted into the protocol called a covariant protocol, which has a much nicer structure. And then after that, we show the conversion between 2 covariant protocols. Okay, so let's begin. So for the port-based teleportation, basically, we consider the following thing. So, you have a resource state for the port-based teleportation, and without loss of generality, this can be represented as a Choi state of some operator O. And this operator O can be anything if it satisfies some normalization condition. And so in this, by rewriting the resource state by this, the teleportation channel can be graphically represented by this left figure. And if you want to calculate the fidelity, basically what you need to do is to connect the input wire and output wire. And if you unentangle these wires, basically you will obtain the last expression shown in the most right figure. Yeah. And by defining the operator pi tilde as by combining O and pi a, and by defining the left part as sigma a, then the fidelity of this teleportation channel can be represented by the inner product between pi tilde and sigma. And we can also show that from the POVM conditions of the pi a, this pi tilde should satisfy some semi-definite constraint shown in the orange box. Okay, so we know the optimal fidelity is given in this SDP form. Right, and also by looking at the symmetry of the sigma a, we can also reduce the problem. So first symmetry on sigma a is a unitary group symmetry. So if you apply U star on the top wire and U on the remaining wire, this state remains the same because maximum entangled state is invariant under U tensor U star, and the other part is just taking a trace. Other part is just a maximum mixed state. So it's invariant under U. And then the second symmetry is on the permutation symmetry. So if you apply the permutation on the wires, then basically it gives you the permutation on the index. And from these symmetries, we can show that the operator X appearing in the SDP should satisfy unitary group symmetry and the permutation symmetry at the same time. And from these symmetries, we can show that this operator X should be a linear combination of the operator called a Young projector. And basically, this Young projector corresponds to the irreducible representation of the unitary group, and which is labeled by a Young diagram. And then the remaining degree of freedom on this protocol is just a coefficient W on this Young projector. And the fidelity of this teleportation, port-based teleportation, can be given as a bilinear form of this parameter W by using the matrix MPBT. Okay. And so this was for the port-based teleportation, and I will move on to the unitary estimation. So for the unitary estimation, I will begin from the most general protocol for the unitary estimation, which is basically represented by a quantum comb in the left figure. So this uses input operations, and this TU hat is basically corresponding to the protocol, measuring protocol. And in terms of the Choi operator, basically this this circuit can be represented by the by this middle figure. And remark that this figure might not be a valid quantum circuit, but we can transform it to a valid quantum circuit in the end. And the first observation on this figure is that about the integral symmetry. And if you insert the unitary operations V and W to the input operations like this, then it should give you the V and W on the measurement outcome. And by moving this V to the other part by using the property on maximum entangled state, then this part should give you the TU hat. So by defining operator T like this, T should satisfy the unitary group symmetry written here. So okay, and then I will rewrite this diagram to the valid quantum circuit in the like this. So first I have this diagram, and I insert the T squared and the T to the minus 1/2 on the figure, and since T satisfies the unitary group symmetry, T squared commutes with a U tensor N. So you can slide this T squared to the left, and if you combine this T to the square with a maximum entangled state, then we can show that this part gives you the valid quantum state, and the other part, the right part, also gives you the a valid POVM. So it is actually the quantum circuit implementing the same fidelity. And from the unitary group symmetry on the T, we can also parameterize T by using the parameter on Young diagram, the same for port-based teleportation. Okay, so finally I will talk about how to convert between these covariant protocols. So as I explained before, port-based teleportation and integer estimation can be both represented by a parameter on the Young diagrams. And if you calculate the fidelity for this one, these fidelities can be represented by these two matrices. And if you calculate this matrix, it actually has a very nice structure that if you define the R matrix here, matrix for PBT is given by R transpose R, and for estimation, it's given by R transpose. So its maximal fidelity is basically given by the maximal singular value of this matrix R. So if you choose the parameters in a nice way, then we can show that these optimal fidelities are the same. And also, we can convert the maximal eigenvectors by just applying the matrix R. Okay, so I will conclude the talk. So in this talk, we show the equivalence between port-based teleportation and the integer estimation, and via covariant protocol. But this approach might have some disadvantage that covariant protocol may require more resources than the non-covariant ones. And the example is that there's a work by Ha et al. Showing that using the adaptive strategy, you can do an integer estimation in a very efficient way by using the no auxiliary qubits. So the future work is that is there any efficient conversion between integer estimation and port-based teleportation? Okay, that's it. Thank you very much.
Thanks a lot, Satoshi. Questions? I can start off the questions. In the very beginning, when you applied this to the optimal coefficient in the second order asymptotics, and you determined that to be d to the 4, and when you have the standard protocol where you restrict the state to EPR states, you get d squared.
Yes.
Do you have any? Does the unitary estimation picture give you any intuition why this is d to the 4th for a fully optimal state?
Thanks very much. So maybe one intuition that why this coefficient should be, sorry, I will go back, should be d to the 4th is like, so basically, so this result can be translated that if n is scales like a d to the square, then fidelity is basically given as a constant. And so this d square is basically the number of degree in the unitary group. So intuitively, it shows that since unitary operation has a d square, d square parameters, you should at least call the d square times of the input unitary. And this is why you should obtain the d to the 4th in the end.
There's a question over there.
Hi. Just a quick question. I wanted to ask about conceptual understanding of the equivalence of these two protocols, because one of them is about unitaries, and the other one is, I thought, was about states. How do you understand that, conceptually? So it seems like the inputs of the two protocols are different things.
Yeah, thanks. Yeah. So maybe one good way to consider the conceptual, similarity, maybe you should go back to the equivalence between this universal programming and the integer estimation. And so if you have a port-based teleportation, you can implement the universal programming. And if you have an integer estimation, you can also implement the universal programming. So by this connection, these two tasks are connected. And the non-trivial part is that if it's a optimal construction or not. And for the integer estimation, we can show, it is already shown that, integer estimation gives the optimal integer programming. But for port-based teleportation, actually, it's not optimal, and we need, one core more to implement that. So, yeah, I don't know if this clearly answers your question, but this kind of connection exists.
And a quick question.
Thank you very, very much for the very nice talk. I have one question about a technical point. So somehow, I guess you were talking about covariant protocols for unitary estimation. But you didn't make any assumptions, I guess, about computational efficiency or whatever. So the output of that is in general just a description of a unitary, right? Basically a set of real numbers. So how do you deal with the fact that in principle, you know, if of course there's like a representation of the unitary group on that output, but it's infinite dimensional in general. How did you deal with that?
So technically, yeah, thanks very much. So technically, we assume the infinite amount of computational resource. So basically, we can deal with a continuous POVM. So the output of this POVM is just an element of the SUD. And so if you want to discretize it, maybe one way is to utilize unitary TDN design. Like so, if you replace this output of U hat with like a discrete set of unitary group, which forms a unitary N design, basically it gives you the same performance. So yeah, in principle, in this way, we can do that.
Okay, let's maybe conclude this talk, and thanks Satoshi again. And we'll take a 3-minute break.